Hello, friends. It's time to talk about potential energy in electric fields. Let's do that. So, how this works is exactly how it's worked with gravity, where the change in potential energy is negative the change in kinetic energy, and the potential energy plus the kinetic energy at any point equals the total energy. That's the most important part. Now, you don't need to know this next part. You need to know the result, but I will tell you that the potential energy formula comes from taking the infinite sum, which we call an integral, of the force times the distance, dx, or change in distance, which is, of course, the work done. Force times distance is work. And if we add that up, like we have a force, electric force, times the distance, and then we have another smaller force times another distance. And then we have another smaller force, like the force decreases. We can just add all those up and we get the work done. And negative the work done is potential energy. So for the electric force, which is given by this equation, which we know very well, the potential energy is just that times dx. Oh, sorry, we would change it to r. Sorry, we would use r as the, sometimes you use x, obviously, sometimes you use r, sometimes you use y. For the equation, we're using r as a radius. We would get kqq over r. So a few things. One, of course, energy is in joules. E is still field. PE is potential energy. This is a scalar, which means it's just a number, so you must plug in negative. This is not a magnitude situation because there is no magnitude of a scalar. It's either -5, +5 billion, -5 times 10 to the -2. You plug in the negative signs or the positive signs, and that's your potential energy. Awesome. So these things are the equations we're going to use and are the most important things. So I'm going to try to give a nice example here. If I have two protons and I want to put a third proton to feel the field, we can actually go back and label some things, which we should do, to remember that this is the charge creating the field. And this is the charge feeling the field. Feeling force, feeling potential energy. That's this one. So we need both. And so these will be the creators, right? And this is the feeler. And so to get the total potential energy at any given point, it's the same as force, but there's no vector. So it's easier. You don't have to draw vectors. The potential energy at any given point, like at point C, will be the potential energy from charge 1, which we'll call this one, plus the potential energy from charge 2. Just add it as numbers. So you don't have to draw any arrows. Don't forget to draw the arrows for the field or the force, but you don't need to do that for potential energy. So how do we do that? What's the potential energy at point C? Well, first of all, you need to figure out these distances. We'll call this, remember this was x equals 0, d over 4, d over 2, 3d over 4, and this was x equals d. I'm using the same numbers in the blue homework. So this is 3d over 4, and then this is what? D over 4. And in general, this would be, for some general point, this would be x, and this would be d minus x. because that's D. This is x equals 0. So in our coordinate system, this is x, this is D minus x. And we'll use that in a second. But just at point C, I would get what? K, E is the one creating it. E is the one feeling it. So I'll get E squared. Don't forget both of those, right? You need both creator and a feeler to have an energy or a force over 3D over 4, which we'll flip in a second, plus K E creator, E feeler, both positive, 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 positive. And all of these things that I'm saying right now are important to think about when you're doing it. Is it positive or negative? What's the creator? What's the feeler? Do I have both? What's the distance? Have I labeled it? Yes, we have. All right. Please do that, guys. Please don't do it in your head. Please don't skip any of those steps. All of those steps are so important. So I'm going to flip this fraction and multiply. 4ke squared over 3d plus 4ke squared over d. Not d squared. Notice the biggest differences are it's scalar. You need positives and negatives. There's no arrows, but there's also no square in the denominator. Big difference. So we're good, but we do need to simplify. That ends up being 12 thirds, which is 16ke squared over 3d. And for the numbers we used in the homework, these are universal. We need to know these. But I set D equal to 10 angstroms. That was arbitrary, but kind of made some sense. I'm going to plug these in and see what we get. What we should get, I'm just going to multiply it out. 9 times 10 to the 9, 1.6 times 10 to the negative 19 squared, right? Times 16 thirds, and then times 10 to the 9, or divided by 10 to the negative 9, the same thing. So this end up being the potential energy at point C is 1.2288. I'll write it to 1.23 times 10 to the negative 18. And remember joules. We're back to joules. There we go. Awesome. So great. That's just how many joules we have. Cool. And it's positive. That's important. It's positive. It's positive because it's repulsive. If you guys remember, positive potential energy is repulsive, which these are. Negative potential energy is binding energy. You guys remember this? Yeah, which is attractive, right? Now we're bringing this back. That's why I like doing the gravity version, is that we can apply it to this. Great. That's positive. Let's do step 2. Let's derive a general formula for the potential energy at x at any given point. Now, if you remember, there was the charge 1, charge 2. At any given point, this was x, and this is d minus x. And these are both protons, so they're both positive E creators. So we have potential energy from charge 1 plus potential energy from charge 2. If you ground yourself like this, you're going to be so golden. You're going to be good to go. K, E, and we are feeling it with a positive E as well. Positive E, positive E. I like writing the positive signs over x squared plus K, positive E creator, positive E feeler over D minus x squared. The things I'm saying out loud, you might want to say out loud or in your head. And we can't simplify this except for squaring the E's. We could do a common denominator, but I think it actually looks neater like this. So this is our answer, which is clearly the general formula of what we're doing. So what's the potential energy at point A, which is D over 2? Well, that's just going to be, sorry, why did I do squared? Do you see what I did? No, I was so used to squared. I was like, something doesn't look right there. Did anybody catch it? Did anybody? I hope you did. If not, all good. Not squared. I don't know if we need to like write a note to ourselves, but not squared. Perfect. That was a close one. Yikes. Got it. So we're gonna do e is squared. Ah, the e is squared, but the x isn't, right? Because the distance isn't squared. It's only inverse square law for force. And the e is squared because there's two of them. So we can remember why these are squared. That helps us remember what's going on. Ke squared over d over 2 plus ke squared d minus d over 2 is just d over 2, which makes tons of sense. So I get 2 plus 2, because that flips, you get 2 in the numerator, 4ke squared over d, which if we multiply it out ends up being, because remember PE at point C was 16 thirds, so 4 over 16 thirds, so PE at point A ratio to point C is going to be 4 over 16 thirds, which is 12 sixteenths, because I just flip and multiply, and I get 3/4. So that means this is 3/4 of potential energy at point C, which was 1.2288 times 10 to the negative 18. So PE at point A will be 3/4 of that, which ends up being 9.216 times 10 to the negative 19 joules. So now we have our two potential energies. And obviously we can do this at any point, but the reason I did these two is because we can use this. So say the question was this. Say the question was just solve for the velocity at point A if the proton is dropped, which means the initial velocity is 0. That's really important, at point C. Well, what would I do? I would say change in potential energy equals negative change in kinetic energy. Change in potential energy is the final, which is potential energy at point A. So I start at point C. Drawing a little diagram helps. It goes to point A and then it's moving because it's experiencing a force there. It gets accelerated. So it's going to lose potential energy and gain kinetic energy. And it loses potential energy because the force is accelerating it, right? It's speeding up. So the force is in the same direction, both negative, vector, just left, as the velocity. That's important, by the way. This little side note is really important. It loses potential energy and gains kinetic energy because these are aligned, right? So that's the picture. I did that quickly, but that's really important. So pause that and make sure you understood everything I just said there, right? Rewind it for a moment, but come back then, and then to actually figure out the potential energy here and potential energy here, the change was final minus initial, which is A to C, which would be 9.216 times 10 to the negative 19 minus 1.2288. I'm not going to round it actually, times 10 to the negative 18, which gives me, yeah, so this was 3/4 of this. So 1/4 of this will be the answer. So I should get -3. That's a big deal. 3.072 times 10 to the negative 19 joules. So that is the same as the delta KE. So the delta KE is positive 3.072 times 10 to the negative 19 joules from this. And since that is final minus initial, 1/2 mv final squared minus 1/2 mv initial squared equals that. The initial was 0, so that drops out. And so we just get 1/2 mv's final squared. Let's not forget, everybody, that the mass of a proton is given by 1.67 times 10 to the negative 27 kilograms. You can go ahead and write that down in your notes right now. Write that down. We're going to want to know that one. We'll know the mass of an electron soon, too. We're going to put it right next to it. Maybe we'll wait and do that a little more formally. So I get, plug the mass in, boom, multiply by 2, boom, divide by the mass. And don't you dare forget to square root to get V final. equals 19,180.8 meters per second from C to A. Great. I hope that made sense. Now, if we want to do a little more detail, I don't want to go too crazy. The force over distance, X, started off like this and went like that. And a lot of you got that right in the homework. This is point C, this is point A, this is point B. If the force was perfectly linear, it would be bigger. But since it's inverse square law, it decreased quickly. So for those of you who solved for V at point A as an approximation, as VA squared equals 2A average delta X. This is correct, but A average, if you did AC over 2, the acceleration at point C divided by 2, that means you're literally assuming it was linearly decreasing. But it's not, it's an inverse square decrease. So it's decreasing faster, which means this approximation was too large. And you should have gotten that the velocity at point A was 22,210, I think, ish. I can't remember exactly, but something like that. But what did we get? We got 19,180, which makes so much sense because the force decreases inverse squarely, so it's less than our simple linear approximation for the average, right? So this is actually calculating the average acceleration. That's the whole point. Potential energy is the average force times the distance. That's the whole concept of it. It's the intricate adding up the forces over the distance. So I thought that was cool to show you guys that. Last question. Proton, 1 angstrom from an electron. The electron has an initial velocity of 0. It gets pushed away and the force decreases, but the velocity increases. And because the force decreases so much, V asymptotes to some maximum final velocity. And we know the graph looks like this. V as a function of X or time, right, will be some V max because the slope decreases because the force decreases, but it's always pointing in the direction of it. These are both positive. It's going to accelerate it the entire time. It just accelerates it slower so that it reaches a maximum speed. Please remember this. We've done this before. Right? Please recall it, I should say. Recall means you're recalling a memory, right? And remember it for the future, right? This was important. Don't remember the answer, remember how we got to the answer. Force accelerates same vector direction. Decreasing force decreases the slope. Great. So we know this. This is a review, right? We've done this before. What we haven't done before is solving for the precise maximum speed in electric fields. We've done this in gravity. We use potential energy in gravity to do this. So, because remember, delta PE equals negative delta KE, or PE initial, right, plus KE initial equals PE final plus KE final. I actually like this one better. So maybe add this to your equation list that we did at the beginning. So what's the initial potential energy? Well, that's going to be K times the source, positive E, times the feeler, negative E, over the distance, 1 angstrom, not squared, or R, you can call it. I'll call it D, right? And what's the final potential energy? Well, remember at infinity, potential energy goes to 0 because, well, D is infinity, or R is infinity. Because you divide by infinity, you get 0. So potential energy final is 0, right? Because R goes to infinity, or D. I'm switching variables because it doesn't matter. And hopefully you realize it doesn't. Meaning I can call this R or D and I get the same answer. Kinetic energy final is the question. Kinetic energy initial is zero because the initial velocity is zero. That was given. And potential energy zero is K E squared negative over D, and D is 1 angstrom. So I can figure this out. So this simplifies to negative Ke squared. Uh, Anybody else see what happened here? I'm going to get a negative kinetic energy. What went wrong? I'm going crazy. Oh no. Why did I have this? That's not what I wanted to ask. What I wanted to ask was this. I did that too quickly, guys. This is not going to be pushed away. Did anybody else miss that? Anybody else pick that up? Anybody watching this video, I feel a little silly. I'm sorry I did that quickly. That would be if two protons were repulsive, right? So hold the phone. Everything else I just said applied except for this. That would be if it repels. Ready? So what I meant to say is, at what speed do I need to launch this such that its final speed asymptotes to zero and it actually goes to infinity? So it escapes. It's clearly not going to be repelled. It's going to be attracted. That is so funny. Do you see how I went through that whole thing and realized that I would get a negative kinetic energy? And I realized that then that made no sense. I appreciate your kindness for that, right? So the negative force decreases meaning just the magnitude gets smaller. Are we back on the right track? I think we're back on the right track. So we started at some maximum speed and it asymptotes to zero like this. So this is the graph of velocity over r or over time. I'm going to do it as over r. This is still the same, but now our initial kinetic energy is our question. And our final kinetic energy is zero because we want V final to go to zero. We want it to barely escape. And if you guys remember, if we make it go faster, it ends up asymptoting to a final maximum speed, but I want asymptote, this is R, where V final approaches zero. And this is V initial here. And the slope still decreases, right? Um, but is negative, right? Because we have a negative force, but a positive velocity. And the positive velocity steadily decreases with the negative force. And I'm writing Fe here because it's the electric force. We're not dealing with gravity, but this is like the exact same thing as gravity. So I'm solving for the escape velocity of an electron. And a cool question. I think that's a cool question. So I get potential plus kinetic equals potential plus kinetic. I just switched which one I was solving for. But I think that was a cool little lesson right there of, oh, wait, I messed up. Now I can go back and fix it. And now I realize that this is what I'm solving for, and this is going to zero. Awesome. And I just had my vectors flipped around. We're good. So negative Ke squared over 1 angstrom, 10 to the negative 10. That was just given. Not 10 angstroms, separate question now. Equals zero plus zero. Oh, sorry. Plus, 1/2 mv initial squared equals zero. So E total is zero, which of course we know happens when you just escape. You guys might remember that. And I can actually solve now for, I plug in now the mass of an electron. The mass of an electron, let's squeeze that up here, is 9.11 times 10 to the negative 31 kilograms. That's a 31. That's crazy. And so I plug in the mass of an electron here, 9.11 times 10 to the negative 31, and I can solve for initial velocity. Everything else I know. I know charge, I know K, I know this, I know mass, I'm good. So I'm just gonna add this over, poop, and divide by m, multiply by 2. I'm just gonna do that all at once. Not in my calculator all at once. I advise you guys to do this in steps, but I'm just gonna do that all at once algebraically because I don't have any room to write anything else on this page. So I have my energy, potential energy, which is 2.304 times 10 to the negative 18. So this is negative 2.304 times 10 to the negative 18 joules, which means this must be positive. And this is really important conceptually. 2.3, so that's why I'm writing it. 2.304 times 10 to the negative 18 joules to escape. So what we're going to get is some initial velocity, which I'll write over here. So initial velocity will equal times 2 divided by 9.11 second EE negative 31. I get a number that is impossible. 5.06 times 10 to the 12 meters per second. 3 times 10 to the 8 meters per second is the speed of light. So this is impossible. So what this means is that not that we need to go fast, not that it needs to go faster than the speed of light, but that at this point, special relativity matters, which is kind of fun. But what's more important is it needs this amount of energy. And what special relativity does is it translates this energy into an actual speed, which ends up being like 99% the speed of light or something like that. So classical 1/2 mv squared only works for things moving at slow speeds. But this energy is still the same, which is why particle physicists typically talk in energy, not in physical speeds. So this is the energy it needs to escape. And these kind of numbers are gonna be somewhat familiar when we start talking about atomic physics. Anyway, I hope that was not as confusing as I made it. I hope that's simplified. The vectors should make sense, the graph, the setup of the energy, the calculation. I hope this part wasn't confusing, but this part matters the most. The part I'm about to circle in blue, this part mattered the most, right? This was the most important thing, right? And I'm solving for the initial velocity, but really I probably want to solve for the initial kinetic energy to escape. What is the escape energy necessary? Please rewind the video to make it make sense. You can ask me a question. I hope that made sense. That was good. We got this. Bringing back the energy. We're good to go. I'll see you guys in class.